You may recall that in chapter 2.5 we studied three layers: 1M, 1M, limited to 2 million and limited to 1 million. This is in the probabilistic trend family modeling framework. And when we looked at the residuals, in particular versus calendar years, we noticed that they were very highly correlated we noticed that by eye. So it seemed like the process correlation was very high, which is something one would expect. And here we're going to study the three triangles again, but we're going to look at a composite model. So, or composite model, as the Australians would call it and English would call it. So here's 1M, 1Mxs1M, 2M. And the first thing we're going to do is actually run the good model for each, and in MPTF. And let's look at the correlations first of all. Here are the correlations. And let's look at the residuals versus, say, calendar years. Now, it turns out that the highest correlation of 0.992496 is between 1M and 2M. So this is 1M. And notice that when you look at 1M, the 98 year is slightly above the zero line, the 97 slightly below. You'll see it's exactly the same in 2M. Now, let's just review what does that mean. It means that if in one triangle an observation is above the trend line, the probability that it's above the trend line in the same cell in the other triangle is not 50%. It would be 50% if they were independent. In fact, because of correlation 0.99, the probability will almost be 1. So you can see there are very high process correlations. This means that in estimating this particular model now, when you estimate the parameters for one line of business, or for one layer, I should say, you're actually you're putting quite a little bit of weight, almost equal weight, on the observations in the other triangle because of the high process correlation. If I wanted to estimate these independently, I can go to the correlation button and set all correlations to 0. So these are the kind of estimates we would obtain in the probabilistic trend family, where we just had all the correlations set to 0. Okay, if we use the estimated correlations, they're very high. The way to design the optimal model is reinstate all parameters, optimize across the lines of business, and you'll see, for instance, that this drop in the accident year for 1M, we have the same drop in 2M, but not the same drop in 1Mxs1M. So the other thing we found out here is in the composite model, limited to 1 million along the calendar years, has this trend. Notice that the standard deviation is also much lower, were you to estimate this model for this triangle independently in PTF. This is because you're also using the observations in the other triangles. The uncertainty in the parameter estimate reduces substantially. If you look at 2M, you've got a higher trend, but 1Mxs1M, you've got a 0 trend. So now when you use the information in the other two triangles, the trend in the 1Mxs1M is significantly not different, or it's 0 essentially, or significantly not different. In fact, if we estimated what is the estimate, we find that the estimate is slightly negative. Well, let's set it to 0. Okay, so now let's just start again, just to make sure we haven't done anything. So we load the independent models. Now we reinstate parameters, and we optimize and save that as our optimal model. Okay. If we now do the forecasting, but let's suppose we only forecast for the 1Mxs1M, and now we will also get a forecast of the aggregate, which is really a forecast for 2M. So let's do it this way first. So we're using a particular model that relates the three triangles and captures the volatility within each triangle just to forecast each one of these pieces and the aggregate. Now, we'll go back and run the same model again, but this time when we do the forecast, we'll just do the forecast for the 2M. And let's see if the two sets of answers are consistent. So we've got a forecast summary for each, and let's look at them. On the left, we have the aggregate of the 1M and 1Mxs1M. On the right, we just have a forecast for the 2M, which is supposed to represent the aggregate. And you'll see the statistics are almost the same. So the model, in a sense, is kind of consistent. We've used it to forecast the 2M, and then we used it to forecast the 1M and the 1Mxs1M in the aggregate, and we've got consistent answers. Now let's suppose something else here. Let's suppose one guy in the company says, well, in respect of the current year and the prior years, we should limit our losses to $2 million. In other words, any individual loss exceeding $2 million, the reinsurer will pay for, suppose. So what this person does, he creates a triangle limit to $2 million and uses it to calculate reserve distributions, just like we have. Obviously, you'll have to have access to this product, because to do it in a statistical package would be very, very time-consuming. It would take you, I don't know, I guess several months or perhaps years. So, and he obtains that the coefficient of variation of his net reserves, given this reinsurance arrangement, is 11%. Another person in the company says, oh, sorry, this is for the 2M. Yeah. Another person in the company says, no, $2 million is too high. We're not ceding enough risk. Let's limit our losses to $1 million. So any loss exceeding $1 million will be assumed by the reinsurer, and he creates a triangle limit to $1 million, and he gets a coefficient of variation which is about the same, 12%. So it seems like when you change the attachment point for the individual losses, you've not reduced the coefficient, or you haven't changed the coefficient of variation of the net reserves, net of reinsurance, for the cedant. Therefore, the amount of capital the cedant would need above the mean is the same in each case, because it only depends on the coefficient of variation, assuming the distribution is log normal, which in many cases is a good approximation to the sums of log normals. Let's look at another example. Here we have an example with layers, and the client created these layers. And we'll go to composite models or composite models, DS1. We'll run the model optimal. Let's see what the layers are. These are huge triangles. You can see they've got, I guess, about 49, 50 development years. Now, so we've got the layers 0 to 25,000, 25 to 50, and so on. Also represents the ground-up data. If we look at the correlations, and you'll see the correlations kind of make sense. If you look at the layer 75 to 100,000, its highest correlation is with the all, which is this row, this column, 0.5699. The next highest correlation is the 0.505 here, which is 100 to 150, and the next one is the 50 to 75. So it bears highest correlation with its nearest neighbors. If you look at the model structure, if you look at the development year patterns or trends, 0 to 25 peaks at development year 1, 25 to 50 peaks at development year 3, 50 to 75, so it shifts to the right. So the higher losses are paid further out. Kind of makes sense. If you look at the calendar year trends, just about for each segment, for each layer, there's a change in trend between the second quarter of 97 and the third quarter. And for example, for the 0 and 25, 0 to 25, 25 to 50, and ground-up data have the same trend, not just change in trend in the same period. So as you keep on moving to higher layers, you can see that the change in trend is always 97 second quarter to third. If I forecast here, system has to keep track of now 24.8 million correlations. Remember, each triangle is about 50 by 50. That's its dimensions. It's got about 50 development years, 50 accident periods. So each triangle we need to forecast about 1,036 cells. And the correlations between all the cells within triangles and between triangles amount to about 24.8 million correlations. Anyway, the forecast should speed up once we get towards the end. Excuse me. And what we find again is the same phenomena. If we look at the forecast summary, then for the ground-up data, the coefficient of variation is 4%. For 0 to 25, the coefficient of variation is 4%. Of course, 100 to 150, which is 50 excess 100, I don't think the correlation is 4%. No, it's 9%. What about the coefficient of variation I meant? I don't know, I might have said the word correlation, but I meant coefficient of variation. If you now forecast up to the aggregate of 100,000, so let's remove these data sets. So these data are additive, so we're forecasting to limit it to 100,000. You'll see that the coefficient of variation is still 4%. And we have plenty of examples of this. I think some examples in let's see, which chapter would that be? Yeah, so there are additional examples in Chapter 5, and you'll see some of the examples in Chapter 5 we observe the same phenomenon, that as you change the attachment point, the coefficient of variation for the cedant of the net reserves out of that reinsurance scheme is invariant, essentially. Thank you.